Sciences in Romania, and part of my team is really based in Bucharest. And since the beginning of this year, I'm also trying to run a company. It's called lionanalytics.ai. But the topic for today is about network controllability and some applications we've done. And I just want to tell you how my journey started with this topic. And I started looking at applications in cancer a number of years ago. And my motivation was really in my own family. 3 of the 4 grandparents in our family went through cancer treatments in the last 5 years. And we are not really atypical in this kind of statistics. According to the National Cancer Institute, approximately 39.5% of men and women will be diagnosed with cancer at some point during their lifetimes. And so that means that most families are going to deal with the realities of cancer and cancer treatments at some point during their lives. And one of the most promising developments that we found when we started looking at cancer therapeutics are the so-called precision therapies. And these are based on new generation of drugs that act on very precise targets, triggering a response in the cancer cells. And also about the same time when we started looking at these sort of applications, the CRISPR-based technologies started coming into high gear. And one particular applications that we were really excited and we are now using routinely is this flurry of new data coming in based on these technologies in identifying genes whose knockout targets cell death in tumor cells, but leaves the healthy cells neutral. And obviously they have a strong flavor for therapeutic targeting. And these are called disease-specific, so they can be discovered specifically for a certain disease and even specifically for a cell line. So disease-specific survivability essential genes. So these are genes that are really essentials for the survivability of the tumor cells. And so all of these lead to the opportunity to ask questions about how to trigger a therapeutic response in a disease through a suitable drug combination. And these drugs might even be repurposed from what they are originally designed for, opening the door to this sort of idea that you might be looking at drug repurposing. One extra motivation in doing this kind of work came when I spent 1 year at the Moffitt Cancer Center in the US about 4 years ago. And the reality, again, of seeing how patients are treated and how they go orthogonally through their therapeutics is that they typically get a number of treatment lines. And they go through these treatment lines until they develop drug resistance. And then they are switched to a different therapy line and they continue on that for a while and so on. The problem with this is that each one of these therapy lines has major side effects, whether medical or financial or emotional and so on. And the other point is that it's not always clear on which therapy line to start with a certain patient. So there is this extra motivation and extra question for this kind of research to stratify choosing the therapy line for a certain patient, depending on other things, comorbidities and so on. And even, if possible, personalize this for her particular genetic setup and potentially even do this orthogonally throughout the treatment. So kind of detect even before you have drug resistance set in that there is a need to change the drug combination. So the other line of motivation came really from the emergent diseases, and we are all now going through this COVID pandemic. And for such emerging diseases, the problem is that treatments are needed very fast and drug repurposing can offer a good solution. So this is what I want to talk about today, our work based on structural network controllability for drug repurposing. And I'm going to show some of the theory that we started from. These are things that have done already starting from the 1960s, and I will lead it to where we entered and what we did. And then I will talk at the end about a couple of applications we did in cancer and in COVID-19. So we started from noticing literally 1 decade ago this cover of Nature, and what struck us when we saw this cover was the word complexity, and there is also the word mathematics in there, and there is the word network and so on. And these are arguably not really common words on the cover of Nature. So we started looking at that, and we discovered that this is about this seminal paper of the Parabasi Group. And that's where we started from. And I'm going to open this talk by telling you what network controllability is about. So giving some of these basic definitions and some of the old results leading up to the way we are applying them to medical case studies. So, I mean, on a high level, on a conceptual level, what network controllability is, it's about the ability to change the global behavior of a network through some sort of well-chosen minimal local interventions. And you choose these local interventions in some way that I'm going to talk about in a moment. And you apply some signals, think about you are delivering some drugs to that patient. And then those interventions are going to cascade throughout the network, and they will induce changes throughout the network. And so eventually, the point is that from whatever initial setup you had in your network, you have the ability through these external interventions to change the configuration to whatever final state you want to achieve in that network. And so obviously there are questions: can you do this in practice for any network, and how small these external interventions are, and so on. So that's the kind of questions that we are asking. And I'm opening this up, and I'm giving some mathematical definitions for how controllability is set up. So controllability has been developed for quite a number of different modeling frameworks. It's being developed for linear networks, and that's what I'm typically working with, but it's been developed also for non-linear networks and for discrete semantics, for continuous semantics. There is a theory of control done and quite a bit of work done for Boolean networks, for example, for Petri nets and for other types of networks. What I'm typically working with is this kind of linear dynamical system. So these are networks where you see the signals going through the network as a network where the edges are the interaction. So it's one source, one effect kind of interaction. So when you look at these kind of systems, you can think about them as a directed graph. And so in this picture here, the network itself is this part where I'm saying these are the internal nodes. So these nodes, you can think about them if you have this analogy of the applications in the biomedical domain. These are genes or proteins that you are interested in. They could be specific to the disease. They could be specific to the patient you have in front of you. You could have some sort of representation of previous treatments and other things. So these are the nodes of interest in your network. And then you have these directed interactions. These are always directed for us. There is a little bit of work done for controllability also for non-directed network, but those are maybe less intuitive what control means. So for us, it's always about directed interactions. And these are interactions that, for example, represent the fact that one protein activates another one, or one protein phosphorylates another one, and these sort of things. And so you have these nodes, and you have the interactions between them. And you can represent all of these interactions through this kind of adjacency matrix. You have your directed graph, and A in here is the adjacency matrix capturing who interacts with whom. And these are matrices over the positive reals. So you would have, in fact, over the reals, you could also have negative weights if there is an inhibition kind of interaction. And so these are, in the basic setup, this is a quantitative framework. You have knowledge about the interactions and how strong they are. And so additionally, on top of this, as I said, the point is that you're looking for some sort of external interventions. So this is represented in this linear network framework by having one node for each one of the external interventions you want to apply to the network. And you're going to draw edges from these interventions, from these nodes you are including here, from the input nodes to the internal nodes that you are influencing in a direct way through these external interventions. So for example, you have a drug, and that's represented by this node here. And this drug has two drug targets, and you represent that by one edge going to this internal node and one edge going to the other node. And then you have also maybe another drug, and this one has only one drug target, and you represent it here. So this set of interactions you have here, you represent them through this adjacency matrix. It's obviously of a different dimension, and I come back to dimensions and all that in just a moment. But you have this matrix B representing these interactions from the input nodes to some of the internal nodes in a network. And so then you think about the dynamics of such a linear dynamical system. And for example, you can represent this with a system of differential equations where your variables, you have a vector of variables, one variable for each one of the internal nodes, and you collect that into this vector X. And then you also have your vector associated to these input nodes. And in them, there are some functions that are up to you to choose. These are your external interventions. So you can put some arbitrary functions in these nodes. And that's this parameter U of t thought about as real functions. So overall, you can describe this dynamic of the linear system through, for example, this set of ordinary differential equations where you have two components. One is the internal interconnections between the nodes, how they influence each other through this adjacency matrix A. And then on the other hand, you have this influence of the external intervention you are applying to the network. So when you see it like this, you can define this linear dynamical system through these matrices A and B, and you can see it as this set of vectors. It's supposed to be the time evolution of the configurations of all of these internal nodes. So this is a function defined on R, or if you like on R plus, if you think that this is a time-dependent function with values in R to power n, where n is the number of internal nodes in your network. And then you have this vectorial differential equation defining this dynamic. And like I said, A is the weighted matrix of internal connections, and B is this weighted matrix of the external influences. And you have n by n for this matrix, and you have n by m, where m is the number of external nodes in this setup. Then you have this parameter, which is the input. So this is also a function defined on R, or if you like on R plus, if you think about this as being time dependent and taking values in R to power n. And then you have the initial conditions for your network. So with this setup, you can give this definition that the linear dynamical system, you say it's controllable if for any initial condition and any final condition of the same dimension. So this is, I'm sorry, this should be R to power n here. There is an input that depends on the initial state and depends on the final state in such a way that the solution to this system of equations satisfies the property that at some time point you get into this configuration. So I'm just going to say it one more time. This is really crucial for everything I want to say. So you are going to call a linear dynamical system controllable if there is a way for you to move it from any initial condition to any final configuration through a suitable choice of your input functions. This is all there is to it. And obviously, I mean, this looks, mathematically speaking, a very heavy sort of a definition. It's not at all clear that this can be done for a given network and so on, but I'm going to open that up in a moment. But controllability is about this ability you have to move from anywhere to anywhere through a suitable choice of your external interventions. So you call the system controllable if you can do this, and it's not controllable if you cannot do it. And then additionally, and in fact, this is the version of the controllability that we are using. You also have the targeted version of the problem where you say, you know, as a matter of fact, I'm not really interested in changing the configuration of all the nodes in the network. As a matter of fact, I'm interested in a number of target nodes. And the intuition, if you think about the biomedical setup I explained in the beginning of the talk, this would be our survivability essential genes. And the point being that if you can somehow knock them out, you're going to have a effect on the tumor cells and maybe leave neutral the healthy cells. So the point is that you would like to choose your interventions in such a way that you have an effect on these target nodes, and maybe you don't care so much about some of the other nodes. If there are some nodes that you care about, just include them in the target nodes and define what kind of effect you want to take on them. So again, the targeted version of this problem is that one where you are saying, well, I have my linear dynamical system just like before, but this time the control I'm seeking is just on a defined set of target nodes. And in the general version of the problem, you even have some output nodes, which are linear combination of these target nodes. In the way I'm applying this, I don't really use output nodes. There is going to be a one-to-one correspondence between the output nodes and the target nodes, just to simplify the setup. But in general, the definition applies also to an additional layer of output nodes. So I just included a picture, so we have the standard definitions. Now, when you have the targets, essentially what you have on top of what I defined on the previous slide is you have a subset of your nodes. This is going to give you the target set. And then you are going to, you can also represent these targets in a matrix representation through this sort of characteristic matrix of the targets T. And you're just going to represent it by 0, 1. And then you will say, well, I put on ij1 if the ith target is j. So just the usual, characteristic matrix defining a subset of nodes in a graph. And so with this kind of setup, the notion of controllability is very similar to what I said on the previous slide. You are going to say that this system is target controllable for this target set T if you have the ability of moving from any configuration of these targets nodes to any other configuration of the target nodes through a suitable choice of the input functions. And I have this, written down in mathematical forms, but it really comes down to this. You say from anywhere to anywhere on the target nodes through a suitable choice of the input functions. And obviously, if you are choosing as the target all nodes in the network, then you are back to the full controllability that I defined on the other slide. So this is the notion that we are starting with, and these are things that have been done in control theory literally from the 60s. That is a very well developed for all of these things. These are definitions that have been given already from the very beginning in control theory. And typically there are two questions that people ask, and we are also interested in these kind of questions. The first one is, somebody gives you a system and it gives you this set of available external interventions. And the question is simply, is this system controllable? Is it true that you can move from anywhere to anywhere through a suitable choice of functions that you are applying on these input nodes? So the question is, somebody gives you the system and the external interventions or the external sort of interactions you have available, and they are asking you, can you control the system through these input nodes? The other question is, you only have the internal nodes, and so this is the typical example we look at when we go to biomedical applications. You have the patient, you have the disease, and you have this kind of biochemical interaction specific to the disease and maybe even specific to the patient. And you are asking, well, okay, so I have my system A. Can I choose a set of input nodes? In other words, can I choose a set of drugs? And obviously, I want to choose a minimal one in such a way that this whole setup becomes controllable. So for a system A, we are asking, what's the smallest input B in such a way that AB is controllable? Right? And this is typically the question that we are looking at when we try to do medical applications. So I'm going to open up these questions. It turns out that they have had some answers already for a long time, and then I show you how we are getting them to be applicable in the medical domain. So it turns out that these are old things, and there is in fact a very elegant solution. I'm writing here in the header of this slide that it's an elegant but impractical solution. I comment in a moment why is it impractical, but it's a very elegant solution coming already from the 60s. It's the so-called Kalman condition, and it's a very elegant characterization of the notion of controllability. It's saying that a linear model is controllable. I mean here fully controllable. You want to control the full network if and only if the so-called controllability matrix has full rank. And the controllability matrix is this kind of matrix that you are building on blocks. You are first listing part B. So this is the part connecting the input nodes to the internal nodes. then you are listing to its right AB and A squared B, and finally A to power n minus 1 times B. Remember, n was the number of nodes in the network. If you want a sort of an intuitive understanding of what this controllability matrix really is, you have on this block the direct effects of your external interventions. These are modeled through this matrix B. Then you have the interventions that you get one step away. So you have applied something, and then you have one wave of cascading effects. Just you take one internal edge in addition to these external interventions, and that's represented here in AB. Then you have two steps, internal steps in addition to the external interventions, and so on. You go to n minus 1, and obviously you don't need more than that if you are not to repeat any nodes. So that's somehow the intuitive understanding of this controllability matrix. And the reason why I find this result really elegant and very appealing is that it's a switch from a notion that is fundamentally based on ordinary differential equations. And I would say that on that level of the definition of based on equations, it's not even clear how would you approach, because it's such a strong condition going from anywhere to anywhere, and the choice of the input functions is arbitrary. It has a lot of degrees of freedom. But it turns out that that problem is really equivalent to a very simple, elegant condition on linear algebra. So this switch from ODs to linear algebra is what I find really elegant in this condition. The problem, I mean, if you start thinking about applying this in practice, for practical applications, it's all about knowing these matrices A and B. And let's say that matrix B is maybe not such a big of a problem because you are choosing your interventions. Maybe you're only given A and then you get to choose B, or maybe it's even B is given to you. But the problem is with this matrix A, if you are given an already existing system, for example, a disease, a disease and the interactions specific to that disease, this matrix A corresponds to reverse engineering an existing system. And you see, it's a very quantitative condition. You really have to know all the weights in these interactions. And some of these interactions could be so deep in the network that you have very little hope of measuring them, or at least measuring them really precisely. And this is not, applicable just, I mean, this kind of argument is not just about biomedical applications. You can also find other applications where reverse engineering this matrix A is really problematic. So the question here is, how sensitive is the controllability property to small changes in A? Because you might not be able to really measure exactly, all the entries in this matrix A. So if there is a little bit of uncertainty in the weights of this matrix, how sensitive is that? So that's one question. Another question is, what do you do if you actually don't know matrix A, or you don't know it completely? But I'm going to open that up in just a moment. But for now, I focus just on this question: how sensitive is it? And so in other words, what this means is how much is controllability about the numerical setup, and how much is it in fact about the structure of the system? So what I mean by this question, I'm leading up to defining the structural version of controllability. What I'm suggesting here is that when you think about this controllability matrix, there are two different layers. One is the interactions. You have these matrices, and they have 0 entries, there are no edges, there are no interactions between some nodes, and there are some non-zero weights on the edges, or non-zero entries in these matrices, and that's where you have the interaction. So this thing that you have an interaction, you don't have an interaction, that's the layer, the structural layer. And on top of that, you have the numerical layer. And so what I'm asking here is, given that there might be problems with the numerical layer, you might not really have access to it in all precision. How much is it driven really about the numerical layer, and how much in fact is driven by the structural layer? And I mean, at least I was surprised. If you haven't seen this before, you might find this surprising, that in fact, it's all about the structural layer. The numerical layer plays very little role in this kind of problems. And this is highly satisfactory, I mean, for computer scientists, because it is then really about graph algorithmics and other things in this sort of problems. So I'm opening this up, and I'm defining what seems to be it looks like I'm taking a lot of freedom with this notion, and I'm going to define the notion of structural control. And again, this is one of these notions that have been in control theory for a very long time already, so definitely not our contribution here. So I'm saying that a linear model defined just like before through matrix A, through matrix B, is structurally controllable if there exists a suitable numerical assignment for the non-zero values of A and B in such a way that the system you got becomes controllable. And I'm going to say this in a different way, again, because it's so crucial for what I want to build up to. So you are given a linear model AB, and so this linear model is going to be given to you again with two layers. Structural layer, you have some interactions, you have some non-existing interactions, and you have the numerical layer. And I'm saying, hey, this system is structurally controllable. If the numerical layer, you can modify it however you like, as long as you don't modify the structural levels. Wherever you had an edge, you can modify the weight of that edge. But don't add edges, don't remove edges. And if you take that freedom of modifying the numerical layer and you get to a system that's controllable, then you are going to call your original model structurally controllable, because this one, the new one, has the same structure as the one you started from. And again, it looks like you might really go very far away by making these changes. And I discussed that in just a moment. It turns out that, in fact, they are very close when you take this freedom of modifying the numerical setup. The key advantage of looking at this kind of notion is that all of a sudden you focus just on structure and not really on the detailed kinetic setup of your network, which might be problematic. For example, some of the networks that we are working with are literally consisting of tens of thousands of interactions, and assuming that you have the precise kinetic setup for that kind of purposes is impractical. So that's a key advantage. You focus on structure, not on this one. And the other one, from a mathematical point of view, is that you switch from linear algebra and thinking about full ranks of matrices to graph theory and graph algorithmics, which again is very appealing to a computational scientist. And so it turns out that this notion has been clarified already in the 70s. And this is, again, a very elegant solution to the problem, and this time even has a very practical appeal. So there is this result proved by Lin in 1974, and then in a different form by Shields and Pearson in 1976. And what it says is, if a network is structurally controllable, then it's controllable everywhere, except something that I comment in a moment. So what this result says is that, right, the natural problem to think about is controllability, but controllability is all about, you know, differential equations, and you reduce it to ranks of matrices, and there are all these numerical difficulties I suggested. And then on the other hand, you have this structural controllable version of it. And what this result is saying is that the moment you are structurally controllable, you are also controllable everywhere for all numerical layers, except a so-called thin set of kinetic setups. So if you think about these kinetic setups as being, entries in a multidimensional vectorial space with one entry for each one of the edges, right? You have a weight for each one of the edges. And you think about those numerical setups where you have exceptions to this result. That kind of set is thin. This is a notion that comes from complex analysis. And what it means is that, I mean, a consequence of being thin is that it has Lebesgue measure 0. So it's really, in other words, if I were to just paraphrase this, you would be very, very, very unlucky to get such a kinetic setup where you contradict this result. And if you had one, even an epsilon change in some of your parameters, that kind of change that goes beyond the precision level you have is going to make your network to come within this result. So saying it just one more time in even slightly different terms, what this result is saying is that when you study controllability, it's enough to study structural controllability. They are really the same notions, except some very unlucky setups, and those setups are extremely sensitive to epsilon changes. So you can focus really, when you talk about controllability, you can focus on structural controllability. That's the important layer and not the numerical layer. And so going back to this, where we started from, with the cover of nature and all these things, what they did was a very elegant and efficient algorithmic solution to find a minimum set of driver nodes that you need to control the full network. And what they observe is that the problem can be reduced to maximum matching in unweighted bipartite graphs, and this could be done with a time polynomial in the size of the input problem. So all of these things lead now to these results that we started from. And so this paper by Liu gave this solution to find, to really solve the full controllability of a network. And they actually ran this on a number of networks. And when we started looking at this, what we noticed, and I want to highlight here, is these numbers. And the way you should understand them, and obviously all of them on this column, is that if you want to gain full control over this particular network, it's a regulatory network for East, you would need to apply direct interventions on 96% of your internal nodes, or on 82%, or on 75%, or on I don't know, 20%, or things of that nature. Now, if you think that it's all about drug delivery, if you want to apply this to the medical domain, that would mean that you build up your networks, and these are maybe thousands of nodes, or maybe even higher than that. It's completely impractical to think that you could ever apply a number of drugs which is on this scale, a big percentage of the internal nodes. So in that sense, what came very clearly out of this is that while they do have a very elegant and polynomial time solution to the full controllability problem, this is nowhere near practical in terms of drug combination identification and maybe drug repurposing. So then we started looking at target controllability. We discovered that this in fact was defined already a long time ago. And I mentioned this just a moment. Now I just bring it one more time up to the slide and just remind you that target controllability is about the ability of changing the configuration of a small part of your network. You have a set of target nodes, and it's all about how can I influence these ones? How can I move from any given configuration to any configuration I want? For example, from a configuration associated to a disease state to a configuration that's associated to a healthy configuration. And for target controllability, there is exactly in the same way it's been defined for a long time, the structural part of it. And again, the same result applies in here as well, that it's not, and it comes from the same set of results from the 70s, it's not about a numerical setup, it's about the structural layer when you talk about target controllability. So you can literally forget about the numerical setup and focus on the graph structure behind your system. And so you all of a sudden get a problem in terms of graph theory. So finally, looking at how do you solve this algorithmically for structural target controllability, you are given a system A, B, and you're asking, is it T controllable for a given set of targets T? I'm only kind of flashing this result just to make the point that this is all about some graph properties. It's about a set of K paths starting in the driver nodes and ending in each one of the targets nodes. So you are covering them with paths, and there is this extra property that no two paths intersect at the same distance from their endpoints. So I'm not going to stay too much on this condition. I'm just showing it to point out the fact that it's now in terms of graph theory and graph algorithmics. And that's where we started from. Just as we were preparing our first set of results, we found out that there was a paper just freshly published at that time, coming from the same group, where they took they took a focus on exactly the same kind of notion, target control of complex networks, and again applied to a number of networks, some of them medical, some of them social, and some of them energy networks, and so on. But what they did in this paper was they gave a greedy algorithm. So they gave an approximation. If you think that the problem is, hey, find the minimum number of drugs that you need to target control a certain network, what this paper contributed and demonstrated in a number of networks was a greedy type of approximation. So that's where we started from, and we started looking into more details on this. And the first question we asked was, okay, so that paper contributes a greedy approximation, but nobody ever clarified whether an approximation is even needed. Maybe we can come up with an exact solution, and how hard would that be? And these are some of the results we did. The first one was to prove that in fact the target controllability optimization problem is NP hard. So if you want to minimize the number of interventions you apply to a network to get it to be target controllable, the minimization part of it is NP hard. And so that kind of clarified that you do need approximations, and we gave what we believe at this point to be the fastest heuristics algorithms and the best approximations results in terms of coming close to the minimum. And also we did a version of this problem where we said, well, okay, so it's about minimizing external interventions, but we would like to maximize the use of FDA-approved drugs. So what this translates into is you are also having a set of so-called preferred nodes. You would like to use those for your for your interventions, because you know that you have drugs acting on those nodes. So it's about minimization of drugs, but maximization of as many as possible FDA-approved drug targets. And so then we build on this, and we build our own software, and I'm going to open that for just a short while in a moment. And we demonstrated this approach for several types of cancer, and also very recently we have a paper this summer in COVID-19. And some of these were presented, in fact, one of these papers was in fact presented a few years ago in CMSB, and it was rather well received there. And there is this application in cancer that was also well received on the oncology part. So here is how we did it. Go ahead. Yeah.
Sorry, just say 10 minutes left.
Yeah,
10?
Absolutely. Yeah, okay. Thank you. Thanks. Yeah. So just one slide to show you the setup of the target controllability as an optimization problem. You are given the disease network, you are given the matrix, and you are given also the target nodes, and I'm showing it here through this characteristic matrix. And the output is going to be, you want to identify a matrix B in such a way that M is minimum, so that's where the minimality of it is coming, and you want to get structural controllability, and that translates into something that I'm not defining on this slide. It's called structural rank, and it's got to be exactly K being the number of target nodes if you want to have target controllability on these nodes. So that's how you define it, mathematically, and it turns out that the problem is NP hard. And then we just said, okay, fine. So we go now to approximation algorithms, and we are driven by the applications in the biomedical domain. And the input controller is this. It's implemented through drugs, but we want to be realistic. We don't want to predict super drugs. So we don't want, for example, to choose external interventions that would have lots of targets inside the network. Drugs don't really have all that many drugs. And a number of other constraints, minimize the number of drugs, and have this sort of set of preferred inputs because you want to maximize the use of FDA-approved drugs. So we formalized all of these conditions, again, in terms of optimization problems, and it turned out that all of these versions of the problems, as natural as we found them, they remain NP hard. So there was no escape from going to approximations. So I just want to show you briefly in a few minutes how we did this when we applied them to cancer, and then if I still have time, just 2 slides for COVID. So for cancer, what we did in this particular paper, and we have some other studies since then, but in this paper, we applied it to 3 cancer studies, and this was done for breast, for pancreatic, and for ovarian cancer. And in each case, we've done the same kind of study design. First of all, we said, okay, so what's specific to this disease? In other words, what are the seeds that we are going to use when we generate a network? So this would be disease-specific genes, proteins. These would be drivers and typical mutations, and what kind of drug targets you have in the standard therapy lines for this disease. And then we would have, for each one of these diseases, we would have the targets. These would be the set of survivability essential genes specific to this cancer. And in fact, we found even specific to certain cell lines that we were studying for this. And these are coming from this sort of CRISPR-based experiments. And then we built somehow the directed protein-protein interaction network around these seeds and these targets. And then we did the network analysis. We've done topological analysis and systems controllability analysis to find out what kind of FDA-approved drug targets would give you control over these essential genes. So in other words, what kind of drugs we predict might be relevant for this disease. So typically the results look like this. This is a picture taken from the breast cancer study. So typically this would be like this. You would have on this part of the picture, you would have the survivability essential genes specific to this disease. And on this other side, you would have drug targets. And you would say, okay, this drug target controls 5 of these, and this one controls 4 of these, and this one controls 4 of these. So you even get a ranking of these input nodes in terms of how many essential genes each one of them controls. And we select these ones to be really drug targets, and then we take a look at the drugs to see, in terms of validation, did we find something that's known to be used in breast? And some of them, the results for this breast cancer study were mixed. Some of them were indeed used. We found drugs that are being used in standard therapies for cancer. This is a drug called lapatinib, and it has a number of target genes that we found also in our analysis. And we found also a number of other drugs that are being used in other diseases, and maybe they have this appeal of drug repurposing, which was the whole point of this study. And then to do all of these things, we had to build our software, and this is the NetControl for Biomed. It's freely available at netcontrol.combio.org. It's been approved for publication just a few weeks ago in bioinformatics, the 2021 version. We have a version from 2018, I think. It was in BMC Bioinformatics. And so this is open source, free to use. It's web-based. You can go in, you can have an account, or you can use it as a guest account. You can collaborate with other people on the networks you are building. It has some visual components, and it has a lot of databases that we have collected, and you have them available to build your networks. We have protein data from a number of standard databases. We have interaction data. We have essential gene data from tens of cell lines. And we even have drug and drug target data. So you really go all the way to identifying combinations of drugs. And we have the ability to generate networks, and we have the ability to analyze networks in this code, in this software. So finally, just the last thing I mentioned very quickly, this is very fresh. It's a paper that is currently under review, and we hope to have this available later this fall for COVID. What we've done is based on a set of data that came in the beginning of this year in Cell. And that data was as a result of a study on genome scale loss of function screen. So what they did in this paper was they identified and even ranked in some way the host factors that are required for this infection with SARS-CoV-2. So in other words, if you knock out these host factors, those cells are resistant to infection with SARS-CoV-2. And they did these studies with a number of techniques, some of them based on CRISPR, but they also did other things. And they did studies on a multiplicity of infection on a low level, 0.01. This is not visible. It's supposed to be 0.3 in here. So a kind of a more severe level of infection. And so, this was ideal for us because it gave us our target genes. So we could do exactly the same study as for cancer, but this time we would apply the controllability using these ones as targets. And we found a number of things. So we found a number of drugs, some of them approved drugs, some of them investigational drugs, some of them are in clinical trials, and people have documented them quite well. So it's again a bag of mixed results. And there is the preprint is available on Archive, and hopefully in later this fall the full paper is going to be. So that's essentially what I wanted to say. Just one slide with perspectives to wrap this up. At the end of the day, you do these studies, and one question that you have to ask, we are asking ourselves, does it work? Does controllability really work in drug repurposing? And the fact of the matter is that it's still not sufficiently clarified. We can do these computational studies, and there is a very rich set of predictions that we typically get out of this. There is some evidence that this could work. There is one that literally came just last week. I was very happy to see this because I could include it on this slide. Some people actually did network controllability analysis, and then they went to the lab and they checked their drug predictions, and some of them worked. And this is for some form of leukemia. There are also other demonstrations, again, coming from the Parabasi Group. This was done on C. elegans, and the point of this exercise was to look at the neuronal network and how it's connected to muscles, and to identify which kind of signals you need to apply to literally drive or ride this worm. Make it go to the right and make it go to the left and so on. selecting your signals based on controllability. So that was also a sort of a demonstration. But in practice, I think that we need more evidence that this actually works. Lots of opportunities. We are very excited about this. Lots of ideas that we still have to apply simultaneously for this kind of multi-clone tumors and patient stratification. And we have some study now on 2 types of cancer where we do this on a personalized fashion and thinking about drug resistance and so on. These are some of the people that contributed to this study throughout the years. The project has been funded by a number of funding agencies, both in Finland and in Romania. Eugen Zeisler is the main collaborator I've had in this project on all these algorithmics and computational complexity results. Krishna was our bioinformatician for a long time on the AMI, on the hardness results, on the software Vladimir, on the earlier version, and now Victor Popescu on the new version. Cristi Gratie has been on the heuristics, on the approximation results. Nicoleta is a PhD student in Bucharest. She's working on the COVID study, and lots of other people from a number of countries working with us in a number of issues, especially this software. This was done by a very young team distributed in a number of countries. So this is what I wanted to say for today. And yeah, thank you once again for the invitation, and I'm happy to take any questions.
Thank you very much.